Hello everyone. This is chapter 9. We're going to look at section 9.1 correlation and then 9.2 regression, and then that is the end of our syllabus. So a correlation is a relationship between two variables. So we can represent data by an ordered pair of XY values where X is independent, or what we call explanatory, and Y is the dependent or response variables. So we're familiar with the Cartesian system and the X and Y axes, so we'll be looking at that. And here's an example. If you conduct a study and look at the number of hours a student spends studying and their respective grade, number of hours is independent. That can change. It's under their control. And their grade is dependent upon how many hours they study. So, for example, you would assume that if you increase the study hours, then hopefully your grade would increase as well. And so when we gather data, we form what we call scatter plots, which are just plotting the points in the coordinate plane, the Cartesian system. And then we could predict whether we have a linear relationship, and that's all we're going to be concerned about, between the two variables. So for example, a negative linear correlation, when we say positive or negative, we're referring to the slope. But if we have the X and Y axes, let's say a scatter plot with a negative correlation might look something like the following. They won't line up perfectly, okay, but they'll suggest a trend, okay, that's negative. Or a positive linear correlation would suggest a positive slope. But again, they typically will not line up perfectly, but something like that, suggesting that the slope is positive. You might have something where it looks like there's no correlation. So, just all over the place, right? There's no straight line that suggests that there's any trend in the data. Or you might have a nonlinear correlation. One of the famous correlations is, with respect to populations, is what we call a logistic growth. Population increases, so we've got all these points here, and then it's going to level off at some value. So that's a logistic growth. But in any event, we're only considering the first two, positive and negative linear correlations. What determines if there's a correlation is what we call the correlation coefficient. And it measures both the type of correlation, positive or negative, and the strength, if it's a strong correlation or a weak correlation, or there's no correlation. And the correlation coefficient, the population, we use this Greek letter rho, but we use R for the sample correlation coefficient, and that's what we want to be able to calculate. So here's the formula. It looks really intimidating, but if you break it down, it's not all that bad, because N is the number of data pairs, as mentioned here, and then all of these summations are just obtained by a little table that we're going to construct. And they're just the sums of the x's, the sums of the y's, the sum of their products, and the sum of their squares. So we'll see in the next example how to break this formula down. And the range of values is always between -1 and 1. And if it's close to +1, there's a strong positive linear correlation. If it's close to 0, we say there's no linear correlation, or it's very weak. And if it's close to 1, there's a strong negative. Usually about 0.8 or -0.8 is the region we say that the correlation is strong. Like, for example, here, -0.9, if that was our correlation coefficient, we'd say that that's a strong negative linear correlation. 0.4 is somewhat of a correlation, but it's very weak. This would be a weak positive. But 0.8 again, that's about the region where we start seeing that it's a strong correlation. This one would be a strong positive. Okay, so the next page has an example of how to calculate that correlation coefficient. And they want us to draw a scatter plot, find the correlation coefficient, and then describe the relationship. And we're going to look at that scenario of hours spent online and your test scores. So, use Course Compass was years ago, actually. Now it's My Math Lab, as you're familiar with. So this is the data, and you can make a sketch of the data. So we have I'll do it right here, so this would be part A. So we'll have our vertical axis. And actually, I'm going to put a little break in the axis. And so we'll indicate a break in the axis. Because I want to start at 40 here. And I've got to go up to almost 100, so let's see, 50, 60, nope, a little bit less than that. So I could say here's 50, 60, 70, 80, 90, and 100. Okay, so just a rough sketch. 0 and 47, be right around there. Okay, so we're going up to 8 hours of studying. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 1 hour, 56 was their scores, right around there. 2 hours, 68, right around there. 3 hours, 79. 3 hours, 73. 5 hours, 87. And 8 hours, 96. Okay, so we can see with that scatter plot there is a trend, right? So probably a positive correlation. Okay, so what we have to do is this. Here's the X column, here's the Y column copied from the data. I filled in most of the table, but here's what we do. We square the X's, so 0 squared is 0. Square the Y's, so 47 squared. Use your calculator, just use the X squared key. 47, hit the X squared, 2209. Then take the product of the X and the Y's, so 0 times 47 is 0. Okay, here X squared, 1 squared is 1, 56 squared, use the calculator, 3136. And then x times y is 1 times 56, or 56. Now note, we gave all the sums here, but you're going to have to calculate them. But we just gave them so we can double check to make sure we did things correctly. Okay, then 2 squared is 4. 68 squared, again use the calculator, 4624, and 2 times 68, 126. Alright, so then you add these columns. And if you add the first column, you get 22. That represents the sum of the x's. You add the second column, you get 506. That represents the sum of the y's. You add the third column, you get 112. That's the sum of the x squareds. Add the fourth column, 38,324. That's the sum of the y squareds. And then add the final column, 1851, and that's the sum of the xy's. Okay, so I know it's a little bit tedious. Feel free to use Excel to do those computations if you want. But that's how we calculate the sums. And then the correlation coefficient. Alright, so the formula, it's on your formula sheet. We mentioned it on the previous page, but you can see it's right here on the formula sheet. Denominator helpful to separate into 2 square roots. First off, you might want to note how many data pairs are there. So it looks like 1, 2, 3, 4, 5, 6, 7 data pairs. So n is 7. Okay, and then the formula. I'm going to fill in the denominator first. So I get a big square root of the n times the sum of the x squareds minus the sum of the x's as a quantity squared under 1 square root. Then similar square root of n, but now the y's. Sum of the y squareds minus the sum of the y's is a quantity squared. Okay, and then in the numerator, n sum of the xy's minus the sum of the x's times the sum of the y's. Okay, so we just got to pick out the right pieces. So obviously n is 7 as we calculated. Sum of the xy's, so that's the 1851. Minus, then the sum of the x's is their 22. Times the sum of the y's, and that was the 506. And that's all over the 2 square roots. The first one, n, which is 7, times the sum of the x squareds, that's 112, minus the sum of the x's, 22, as a quantity squared. Okay, and then under the second radical, n, which is 7 again, times the sum of the y squareds, which was the 38,324, and then minus the sum of the y's was the 506, but as a quantity squared. Now in terms of the calculation, you might want to take this a little bit slow. Calculate the numerator separately, write it down. That's just a straightforward computation, so check that, it's 1825. And then I would do each square root separately. For the first square root, we get 300 under the radical. For the second one, 12 to 32. And then what you could do, so double check that, those are straightforward computations. And then what you could do is maybe multiply the two radicals together. So multiply the radicands to get a single square root. And that'd be the square root of 366, 9600. And then do that computation. So do it any way you like, but that makes it a little easier. And we get 0.95269. I'm going to write them all down. 41649. So you could double check your computations. Okay, so then that's our correlation coefficient. It's really close to +1. So therefore, we say a strong positive linear correlation. Okay, so once we know that there's a correlation, then we can, this is the next section, 9.2, we can determine the line of best fit. That's what's called the regression line. So what we want to do is minimize the residuals, the distances between the points and the line. So if you look at our last example, if we were to try to draw a straight line through these points, it might look something like that. These distances, these vertical distances from the points to the line, those are what's called the residuals. And that's what we want to minimize. And you don't have to worry about the theory or anything, just about how to do the computations. We're going to find that straight line, which is of the form, as we know, the equation of a straight line, y equals mx plus b, where m is the slope and b is the y-intercept. So there's the equation for the slope, and here's the equation for the y-intercept, where y bar and x bar, respectively, are the means of the y's and the x's. And then again, it's the number of data pairs. So we have an example, and used my name in this. Actually, there were 4 of us that worked on these notes together, and they were Mr. Corella, Mrs. Jowsey, Mr. Hake, and myself. And so they made up these notes on this section and just put my name in there. But in any event, we want to know if advertising, the money we're spending on advertising, is worthwhile. And here's a table showing the expenses and the amount of sales. They calculated the correlation coefficients. There's a strong positive linear correlation. Now we want to find the equation of the regression line. So these formulas also, all of these formulas here, are on your formula sheet. Notice that we only want the correlation coefficient. We're not going to be doing the t-test, so you don't have to worry about that. And we want the equation of the regression line. And then we're not going to be doing anything with the rest of that. Okay? So that's all we need from chapter 9. So you can see these are the formulas given. And all we have to do is the computations. Now, we went through and we did the busy work. We already calculated the sums for us, but you would build the table like we did in the last example, getting all of these sums. But here, that's done for us. Okay, so our formula for m, the slope, and you always want to find the slope first, n, sum of the xy's, minus the sum of the x's, sum of the y's, all over n sum of the x squareds minus, in parentheses, the sum of the x's quantity squared. Alright, so let's note how many data pairs we have. Count them up. 1, 2, 3, 4, 5, 6, 7, 8. So let's add to this the fact that n equals 8. And into the formula, n 8, sum of the xy's is 3289.8. And then minus the sum of the x's, that's 15.8 times the sum of the y's, 1634. And that's all over n again, which is 8. Sum of the x squareds now, that's 32.44. And then minus the sum of the x's was the 15.8 again, but as a quantity squared. Right, so once again, in terms of the computation, you might want to do the numerator and denominator separately. Get 501.2 for the numerator, 9.88 for the denominator, and that gives 50.73 for our slope. Alright, now the y-intercept b is given by y bar, it's not b bar, I'm sorry, it's just b. Because the equation is y equals mx plus b. They put a little cap on it. They say y hat equals mx plus b. Because it's an approximation, that's why. But y bar minus mx bar. And y bar is the sum of the y's over n. So that's, sum of the y's was the 1634 over n, which is 8, is 204.25. X bar is the sum of the x's over n, which was 15.8 over 8. So X bar is 1.975. So then B is going to be equal to Y bar 204.25 minus M 50.73 times X bar 1.975. And that crunches out to be 104.06. So now the equation, again they say y cap or y hat is mx plus b. So our equation m 50.73 times x plus b, the 104.06. So now we can predict values of y for certain x values. So it says use your answer from part B to predict what is y when x equals 2.2. See, this is just the observed value. Remember, those, when we draw a line, not necessarily passing through that point. So all we do is we substitute this value of x into our formula for y. So 50.73 times 2.2, and then plus the 104.06. So that gives 215.666. Okay, but then here's something interesting. This value of 3.1 If you look at the range of the x values here, the lowest is 1.4 and the highest is 2.4. So there's no meaningful prediction we could make for 3.1 because it's outside of the range of x values. So therefore, we say that this is not meaningful. It's what we would call an extrapolation, and we can't do that. Okay, so that's the end of the course, and I wish you all the best of luck, and not only in our final exam, but in all of your future academic endeavors.